The next topic that we want to look at is EigrpJune, which is the Cisco proprietary routing protocol. Try to show you why it really would be the preferred one if you're installing in an all Cisco environment. And that's one of the bugaboos about it. It is Cisco proprietary. It's called an advanced distance vector protocol. Uses some ideas from a link state. Cisco proprietary. Won't work on non-Cisco devices. If that's the case, if you have a multi-vendor environment, multiple manufacturers of your devices, we need to go to OSPF instead of EigrpJune. Rapid convergence, backup routes, feasible successors, pre-calculated. So that's some terminology here. Let's look at some of that here. This is an EigrpJune. This has got both IPv6 and IPv4 running on it. So when we do that, I want to go to New York because I've been fooling around here trying to find the one that actually does have multiple routes. So we can show IP route for these things, and we have the D's here, which are going to represent EigrpJune. We have the administrative distance of 90, and then we have the metric, bandwidth and delay. Some of them are pretty small. Some of them get really big. The numbers get really big. We're going to have the formula here in a few minutes. Not that you need to know the formula, but that we have it. It uses these things called K values. We'll show IP protocols. K values here, the metric weight, K1, K2, K3, K4, K5. This is not the value. This is the multiplier. So you notice that we have 5 values, but we only use 2 of them, and the 2 that we use are bandwidth and delay. The router ID, it has to have an ID, and this is the same thing for IPv6. If we were doing IPv6, we have to put in that 32-bit number for a router ID. It has to be manually configured for it. Active timer, distance interval 90, external 170. Internal is the thing that we typically look at for this. It has an autonomous system number, EigrpJune, which means that it'll speak to all the other autonomous system 20s, EigrpJune. If we have 2 of these, an EigrpJune and an EigrpJune, the 10s and the 20s don't talk to each other. We have to use that redistribution command in order to put the routes from one EigrpJune into the other EigrpJune autonomous system. The router ID, the distance, maximum paths, these are the equal cost paths. And maximum hop count here, 100. Variance is a way that we can configure unequal cost or unequal metric, unequal load, unequal cost load sharing. So that if we had one, it was like maybe one was twice as good as the other one. One would get 2 packets and the other would get 1 packet. But we can do unequal, and then we use that with the variance command. Auto summarization, and this is one that you'll see a lot of different ways. And I've got a slide that says why it is this way. The newer systems, auto summarization is disabled. On the older systems, auto summarization is enabled by default. So automatic address summarization, auto summary is disabled right now for this one. Maximum paths, and these are another configurable value, the number of equal cost paths, because the variance here is 1, which means that all of the costs, all of the metrics are going to be equal for this one. And the routing for the networks, the ones that were advertised. Routing source in the last update, different things that are available in it. I want to go to the topology table first. Topology table here, because this is one where we have, and successors are the thing that you're going to hear called in it. And when you hear, see, read, think, see in the topology table, successors, think successful. One of the things that the slide says was rapid convergence, backup routes, feasible successors. The backup routes are already there. If we look at this one, it says one successor or one successful route, one route that we can use. But we have 2 of them listed here via the 10.1 and via the 10.5. When we go over here, we're going to have a couple of different things here that are advertised. 358, we're going to have the feasible distance, and we're going to have the reported distance. Couple of kind of different terms. The reported distance is what the guy at the other end that gave us this information told us. The router at the other end told us that it cost them to get to this destination. What we do then is add the cost to that resource, and then we have the feasible distance. The feasible distance here, it says feasible distance FD is 307.3024, which is going to be the best that we have. I want to draw an arrow. I'll get towards one other thing right here. The P here, if you go up here, is passive. Passive is what we want to see. If we have an active, it's actively seeking to find routes. P for passive means that we found it, it's stable, not looking for the information anymore. And in this one, we got several of these that have multiple paths. 3328, 3072 is what it was, and we'll look at some of these just in a second. I want to scroll something else here, but we have a lot of one successors here. We don't have two successful routes. We can have that. We'll look at another one that'll have multiple successors. But we have those capabilities. If we have, and you get the ugly routers here, if we have these guys connected together, router A, B, and C, we're going to have a cost to get to him, bandwidth and delay to get to him. He's going to have his own cost to get from here to here. What this router B sends us is this cost, which is going to be our RD, our reported distance, what it told us that it cost. And this is and we'll just say my cost. So the reported distance plus the cost here is equal to the feasible distance, and that's how that's calculated. We rely on the other end, or the reporting device. That's why we have two numbers here in the topology table: the 3328, the feasible distance, which gives us the success or the successful route, feasible distance 3328, and then we have that's being used. This is the one that's going to go in the route table. The reason converges so much more quickly, these backup routes stay here, so that if this route now suddenly goes down, this one just gets elevated to the route table, so it doesn't have to go through it. EigrpJune doesn't have to go through the calculations again. And then if I do the show IP route again, we have the routes that are put in the route table. We don't have any. We'll look at another one that has some equal cost routes. In this one, now let me drag this back over here, and we are on New York, and I want to do this because we have a couple of them, and one of them up here had some pretty small numbers. It has a route. I can read it and still see everything else. It has, let me move that. It has a route to 10.10.10.0, and I got to figure out where these things are. 192. 10.10.10 network would be over here on this device. Yeah, and that kind of makes sense. We've got a relatively low cost of 3328, and the reported distance is 3072. So this one is saying, hey, it cost me 3072 to get there, both gigs. And this one, we then add our cost to get here, the 2 gigs, and we get the feasible distance of 3328. The other one going through 172 to 10.1, which would be this guy down here. Yeah, that was the other cost. The next one, it goes via 172.16.10.5. 172.16.10.6 would be my address. 10.5 would be the other one up here. So The different costs, we have the different paths. The serials are going to be much slower bandwidth and delay. The bandwidth is going to be a whole lot lower than it would be for the gigabit connections. So the reported distance plus the cost, our cost to get to the next hop, add those two together, and that's what we get for the feasible distance. Feasible distance, and then we have feasible successors. Those are the other ones that are in the route table. Let me get rid of this one. I want to look at. We'll look at one of these others down here. I think this one probably has some equal costs that it can do here. Let's see. Show IP route. When we do that, yeah, we have two routes in here going to 172.16.10, going out to two different interfaces, gig 00 and gig 02. If we go into the show IP EigrpJune topology, then we have the two successors. This is that one down here. Jumped in on it, didn't I? So the reported distance for each of them is the same, which kind of makes sense because it's going to cost the same to get there, and then the feasible distance is going to be in here for these things. We have two successors, two successful routes, two routes that are going to go into the route table. So EigrpJune, some of the capabilities that it has, it is really. Let's see if I missed anything. We saw the topology table. We didn't look at the neighbors, and it just lists the neighbors. The number over here, the 0 and the 1, this is just the order that they were received in. We got the hold up time here. How long is it good before we do a hello time? And if we do another one, you notice that those decrement to get, when we get to 10 seconds, it gets reset to 15 seconds every 5 seconds. The neighbors that we have, the interfaces that the neighbors are on, and these are the address of the neighbor, the router ID that goes on. Each of them for these protocols, each has to have a unique router ID in order for them to. The feature, Cisco proprietary, we got that. Won't work with non-Cisco devices. That's the proprietary portion of it. Rapid convergence, the backup routes, the feasible successors. Successor, again, successor, think successful. Feasible successor is, yeah, it can be put into the route. Incremental updates. After the initial, only updates that affect neighbors are going to be sent to those neighbors. And if you think about it, it's still going to be a cascade effect, but incremental updates are going to be here. Load balancing across equal and unequal costs, and we saw that when we looked at the show the protocols, that the default is equal cost load balancing. We can configure it with a variance in order to make it unequal cost. Flexible design, we don't have any ABRs, area border routers. We don't have any ASBRs. We don't have any designated routers. We don't have any backup designated routers. Does use the multicast protocol, 224.00.10. Classless VLSM works. It has its own layer 4. Uses reliable transport protocol, RTP. It doesn't use TCP or UDP for these things. The packet types, we have the hello packet, the update packet, the query, the reply, and the ACK. And I don't have and you'll probably be happy, I don't have a Wireshark of that. The hello intervals don't have to match on these things, but the K values do have to match, and the autonomous system numbers have to match. I guess we didn't really look at the configuration of it, and again, this has got IPv4 and IPv6 on it, and the IPv6 configuration, like OSPF, is configured on the interface. But for the EigrpJune, the network, and you notice that I've cheated here. Theoretically, you got to put in the wildcard mask. If you don't put in the wildcard mask, what this will do is advertise everything that starts with 172.16, or everything that starts with 10, or everything that starts with 192. You can use that in reality. I wouldn't try it on an examination if you're asked to do that. Wildcard mask. These things still do use wildcard masks. And here, you know, an IPv6 EigrpJune, even though IPv4 is configured on this one, it still has to have a router ID. And let's just to kind of re-emphasize something, show IPv6 route. You'll notice that the vias here, the network and the via serial whatever 2001, those are the links. Via, and this is where I want to get to, the protocol where it's going someplace, FE80, it goes to the address that it uses is the link local address, the FE80 address. So autonomous system numbers must match for those things. This is the auto summarization, hopefully clarification. Maybe clarifying something that you really didn't need clarified, but the EigrpJune auto summarization is disabled by default beginning with release 15.0 revision 1 and 12.2 revision 33. Prior to that, automatic summarization was enabled. We turn it on off with the auto summary and the no auto summary. In the router EigrpJune and the configuration config router, the EigrpJune. Some of the basic components, RTP, some of the things that I think that we've already looked at a little bit of this. Reliable transport protocol guarantees the ordered delivery of the EigrpJune packets. It's the layer 4 protocol instead of TCP or UDP. Neighbor discovery and recovery mechanism uses the hello messages from the RTP, the Reliable Transport Protocol, to discover neighboring routers on directly attached networks. The whole time determines if a neighbor's failed, and these are always the same when we do these things. The whole time, and how long we're going to wait to hear from a neighbor or a device. Is it still there? By default, it's going to be 3 times the hello interval when we do that. The algorithm that EigrpJune uses, dual diffusing update algorithm is the title of it. Responds to changes in the routing topology, dynamically and automatically updates or adjusts the routing tables, and that's why we have the dynamic routing protocols. Calculates loop-free routing information. Feasibility condition here is the reported distance. What the other guy told us it cost him has got to be less than the feasible distance. And I think that kind of makes sense, but that's one thing that gets pointed out in like all of the books. So the reported distance got to be less than the feasible distance. Feasible distance, what it costs us. The K values to determine the best path. These are the things that are used to determine what's going to get there. And again, we have the K1 to bandwidth, K2 load, K3 delay, K4 reliability, K5 MTU. The only ones that are used, and the values, the ones that we saw, are the multipliers, not the value that is used. So bandwidth multiplied by 1 and the reliability by 1. And it's not quite that simple. We will still have the K values are not the metrics. Bandwidth and delay are the default metrics. In the EigrpJune metric, the bandwidth that it uses is the slowest that we're going to use. That's going to be there. And this is one of those. The slowest link plus the sum of all the delays is going to be the metric here. The bandwidth, and we may say, hey, I've got a really fast connection here. Why is it going the other direction? Maybe going the other direction because someplace along the path there is a slow link, and it will then prefer the other path. The bandwidth that it uses, and this is why we get these really big numbers, and 10 to the 7th over the minimum bandwidth in kilobits per second times 256. The delay is the sum of all the delays in tens of microseconds, and then we add those two together in order to get the distance, the feasible distance, or the reported distance, or the metric that we're going to use. The successor route is the best one. The successor, and when we looked in the topology table, successor, sometimes we had a successor and one of them we had 2 successors, equal cost load balancing. The successor is the successful route, the best one, the best route to the destination with the lowest metric. The feasible successor, and we saw that in a couple of them, are backup routes. The backup routes stay in the topology table, and you notice that this topology table is different than the topology table that we saw in OSPF. OSPF uses its topology table in the Dijkstra algorithm in order to calculate the shortest path. Shortest path first, the SPF path, the shortest path. This one, once the calculation's done and we have successor routes and then everything else is going to be feasible successors, they're going to be retained in the topology table so that if the successor route, the one that gets into the route table, has a problem, goes down, interface dies, whatever else could happen to it, the feasible successor, the backup route, gets immediately put into the routing table. That's what is going to make it a whole lot faster to converge than the other ones. The feasible distance, the one I tried to scrawl, much prettier picture here. The feasible distance is the bandwidth and delay using that formula to calculate the metric to get from us to it, from here to there, when we do that thing. So R1, R2, but the feasible distance is the whole thing. The advertised distance or reported distance, and you may see it either way, is what it costs the guy in the middle here to get to, what it costs R2 to get to R3. He then reports that distance to us. So the reported distance is, or the advertised distance, feasible distance, I'm going the wrong direction. R2 to R3, R2 to R3, R2 reports or advertised distance, what it costs him. No, I'm going in the right direction. Confuse myself. The advertised distance here is this cost in here, and that's what gets reported to us. And the whole thing, our cost to get to R2 in here, plus the advertised distance, is what the feasible distance is going to be. What's it going to cost us? So they do depend on each other things, however we want to say that, to get a number of tables and the kind of a progression here, a number of tables in EigrpJune. Selects the primary, the successor, and the backup, the feasible successor, and injects those into the topology table. The primary, the successor, is moved into the routing table. So we have a neighbor table, the list of directly connected and adjacent EigrpJune neighbor routers, and the local interface to exit to reach it. So we saw that in the show IP EigrpJune neighbors. From there we get a topology table. Feasible distance and advertised distance via each neighbor is going to be there. The list of all routes learned from each EigrpJune neighbor and identifies the successor routes and the feasible successor routes. And then we have the route table. The best in the topology table is going to go into the routing table. So first we establish adjacencies with our neighbors. They tell us what it costs them to get to different locations. Reported to us, advertised distance or reported distance. And then from all of those calculations, we're going to take the best of the topology table and put it into the route table to do those things. A dual decision tree and the lost connectivity to a successor. And this is the why is it so fast? Is there a feasible successor? If that's the case, promote to the successor, install the successor in the route table, select a new successor, and install the feasible successor, if any, in the topology table. If the answer is no, place the destination network in active state, because if there's not a feasible successor, then there's probably not another route to get there, because all of those calculations have already been done. So that if something happens to the successor route, the successful route, the route in the route table, the feasible successor gets automatically put into the route. This is the actual real formula down there at the bottom that it uses. Do you have to know this? Absolutely not. It just, I guess, we'll put it in here to kind of I'm going to wow you to see that these things do some pretty complex calculations in order to be able to get there. And again, we're only using 2 of the K values, although they're all involved in here. K1 part 1 times the bandwidth, the K2 part 0 times the bandwidth over 256 minus the load 0. K3 part 1 times the delay, the K4 and the K5 part 0 over reliability plus 0, and it's still going to be 0. And down at the bottom, what is the calculation, the equation for calculating the EigrpJune metric. The routes here, and this is going to be the reported distance and the feasible distance here. So the routes A, D, C, A, D, C, A to D to C, 10 plus 15 plus 5, because we're going to get to the other side of this thing. A to B to C, A to B to C, 25, 35, 40. A to E to C, 25, 30, 35, from one to the other to do these things. So the successor is going to be the one that is the lowest. The feasible successor must have a reported distance less than the feasible distance when we get there. The advertised distance or the reported distance, you notice that we've swapped the abbreviations right here in the middle, reported distance, advertised distance. What that is here, that ABC, B tells us that it costs him 15, the 10 plus the 5 here. The here, AE, tells us it's 30 to get there. And then we add our cost to get to each of these resources to the reported distance or the advertised distance, and that's how we get the feasible distance. The deciphered, and we looked at this already, I think, in the packet tracer. P, the passive, means that the router's not looking for a route. Passive is what we want to see in the table here. A, actively, the status active means that there's some stability and it's actively seeking routes here. The topology table P, and this one we have one successor, the feasible distance via connected serial interface, the things that we saw. The feasible distance and the advertised distance are the two numbers. The advertised distance, what the other router tells us it costs them to get there. The feasible distance, what it costs us to get to the other router, plus what it costs him. So these devices, again, these devices depend upon each other in order to get the true cost from us to the destination and to do the route tables. D, the dual algorithm, RTP, the reliable transport protocol. And in here, the D, to get to a location, the administrative distance of 90, the feasible distance, the next hop, and then the interface that it's going to go out of. Same thing, it's been in all of the route table information that we've used here. And what this is showing is that the feasible distance gets brought down into the route table. The calculation here, how do we actually get that really big number, 10 to the 7th, over the minimum bandwidth in kilobits per second times 256. Kilobits per second is going to give us a big number anyway. And then the sum of all the delays in tens of microseconds times 256. Let's say the minimum bandwidth is 56K, and the total delay is 100 plus 100 plus 2,000, so it's going to be 2,200. The formula here is going to be, what is this, 1, 2, 3, 1, 2, 3, 10 million over 56, 10 to the 7th over the minimum bandwidth, plus the total delay times 256, 178, 571 plus 2,200 times 256, and then the whole thing times 256. So we're going to get some pretty big numbers here in the EigrpJune. Just really big numbers. It's a moderately complex calculation here from one to the other. The EigrpJune neighbor table, we looked at that a little bit. The address of the neighbors, the interface you're connected on, the amount of time left before it is considered down, and at 10 seconds we should get a reset. We should get a new hello message. And I think that we kind of did sort of see that happen when we were looking at these. I'm not quick enough in order to be able to do that. Show IP neighbors. We have the countdown here, 11 seconds, and to 12, 11, 13, 14. So it got reset. 11, let's see how long it goes, to 14. You know, I don't ever see it go under 10. It's obviously not doing it in seconds because 13, 10. So when I reset the 10, and maybe it's because I'm just too slow on the keyboard to make that happen. So we have the amount of time left before it's considered down, the hello, the dead timer here, and then the amount of time since the adjacency was established. How long have we had that information? When did the adjacency get established? The adjacency requirements, active hello packets, the autonomous system numbers have to match, and the K values have to match. Autonomous system numbers in this case is our choice. We pick them. It doesn't matter what it is, but they do have to match so that they share information. And again, if we had an autonomous system 10 and autonomous system 20, they wouldn't talk to each other. All the autonomous system 10s would talk together. All the autonomous system 20s would talk together to create routers, to create routes. We could then redistribute one EigrpJune autonomous system into the other one so that they could share the routing information from one to the other. 6, got to be configured directly on the interfaces, and let's go back one more time. We'll look at this one more time, that it is just like OSPF, configured on the interface. Shall run for this thing. So we have, and this again got both IPv4 and IPv6 on it. So we go down here, the IPv4 address, the IPv6 address, the global address, and then EigrpJune, IPv6 EigrpJune is configured on the interface. Each of the interfaces that are playing in, working in the EigrpV6 are going to be EigrpV6, IPv6 EigrpV are going to be configured on the interfaces. And we do have to have a router ID. Here we go, EigrpV router ID. We established the instance right here with IPv6 router EigrpTen, the autonomous system number that we would have available on it. And all of the show commands for IPv6 are IPv6 has to precede it instead of IP. Can be used without the use of the global IP address. Oh, that's what I was going to do just one more time, just to try to re-emphasize is show IPv6 route, spell route, that the destination, here we go, we're going to this network, and you notice /64, the administrative distance, and a really big number for the metric, but via the FE80 address. FE80 going to be the link local address. And you notice in here it's using the FFFE as part of it. So the Cisco routers will use the MAC addresses, and each of the interfaces is going to have a MAC address. Otherwise, we couldn't get it to a specific location from one to the other. But you can go and calculate those things. I think this is the same one that we did yesterday. We had the 000D0 something another, and these over here, FED1, these over here, it's going out the same. That's why they're the same, because it's going out the same interface via the next hop address. So they are going to be the same, but the IPv6 uses the link local address for all communication with adjacent devices. Differences between the two: IPv6 protocol instance requires an ID, a router ID, a RID, which is just a matter of going in and putting router ID when you're configuring a EigrpP instance of the EigrpP autonomous system. Before it can start running, strangely enough, you have to give it a no shutdown command. It has a shutdown feature, and it is shut down by default. So you have to, in order to start, and this is the only one that I know of, and doesn't mean that it's the only one, but the only one that I know of, that you have to actually give a no shut before it will start. User uses passive interface, EigrpP. Just don't configure it on the interface. And again, passive interface, so we don't want it participating in the process. Uses a distribute list, prefix list command to provide filtering, and a route map command. And route map, these are things that, again, it's kind of nice that they're here, but we're not doing route maps. We're doing just standard routing. We're doing OSPF, a little static, configure, look at static, and then OSPF for a single area. This is kind of a bonus coverage, I guess you would say. You're going to run into EigrpJune when you're in a Cisco environment. Just like in OSPF, we have to use the IPv6 unicast routing command in order to turn on routing for IPv6. It's not there yet. Specify the routing protocol, IPv6 router, EigrpJune autonomous system number, in order to create the autonomous system that then allows us to do the configuration on the interfaces. Specify the router ID, and then finish with the no shut command. Enable it on the interfaces. When we do that EigrpJune autonomous system number, we've looked at those a little bit. I think this is the last topic, which is the troubleshooting of routing issues. And you can probably think of a whole bunch of things, and that could be issues with the routing. One of the things that is kind of handy to know or to have an idea about, and this is just a kind of a summary of a few of them, is what do the characters mean in the ICMP messages. The exclamation point, by now hopefully it means it is good, we got there. The dot means that we didn't get there. The dot is each period indicates a network server timed out waiting for a reply. The first time that you ping a Cisco device, you're going to get the dot. You're going to get it didn't get there. And the reason is that the ARP resolution isn't completed by the time the reply should come back. So it doesn't know how to actually get to the resource. So the first time you'll get a dot and 4 exclamation points. The exclamation point, we're good there. The U, the destination is unreachable error. PDU was received. So destination unreachable, network unreachable. You know, we probably want to start looking at our route tables. Do we actually have a route? Q is source quench. This is the message that says, you're sending me too much data. Slow down. I can't accept all of the data. It's coming too fast for me to be able to process. So this is the one where we stop sending packets. Source quench may be destination too busy to do that. M, could not fragment. A question mark, unknown packet type, and then the ampersand, the packet lifetime exceeded. This would be when our TTL expired. And the one that I've seen comes back, didn't say packet lifetime expired. When I had one do that, it came back and said packet expired en route. And it did. It had created a loop, or a loop had been created just as a little kind of, I don't know, hopefully interesting. We're doing some work on the internal network on the firewall. Didn't want anybody fooling around with anything. So disconnected the firewall, disconnected the information. So if you try to ping there, nothing would happen. The ISP was here and we're here. Each had a static default route. And we've talked about, yeah, we can do that. Everything from us goes to the ISP. And at the ISP, everything to a particular, and I will just say that it wasn't 10.60 because that's a private address. These were public addresses. 10.60.0/24 goes to us. So trying to get there, the ISP would send the information, and they had turned everything back on internally, but hadn't connected back to the outside device. So the networks didn't show up. It would get here, nope, not here. Send it back to the ISP. Oh, it's to this guy. Send it here. Oh, it's to this guy. Send it here, until we actually exceeded the TTL, and you get an error message back that says that the packet expired en route. So common routing issues, the static IPv4 and v6 static routing issues. I'm going to say There can be a lot of those. I think the most common one is that you get to the destination, but you don't give a route back. You have to have the route back in order for it to complete the full path. Standard commands to isolate the problem. Standard commands that we've talked about. Ping, trace route, show IP route. In this case, for IPv6, show IPv6 route. Show IP interface brief. Show CDP neighbors detail. Are we talking? Are we connected? IP neighbors detail. What do the IP addresses look like? Are the IP addresses correct? Is there an entry in the route table for the location we're going from to? Inter VLAN routing issues. Ping checks. Send ICMP pings to check for layer 2 connectivity. Are we connected? And we did these things. What I did lands, part of what I did was break it so that we could try to go through and see what actually happens if we have different configurations issues. But inter VLAN routing, interstate between them, can we get from one to the other? And the other thing would be, is there a trunk port between these guys? If it's between two devices on the same switch, that they're assigned to the same VLAN. If they're not, they're certainly not going to talk to each other. The problem between the devices on different switches, verify that we have a trunk. And, you know, one of the other things to verify, I guess, is that the native VLAN is the same on both sides, that we're not getting all those error messages. Ping from the end device to the VLAN interface. If it fails, verify the default gateway. If unable to reach the internet or the corporate network, verify that the default route, IP address, subnet mask on the switch, all of the things that we've talked about are consistent, that we're on the same network, that the default gateway is correct. Then going to the internet, can I get to the DNS server? Can I ping the DNS server? Is there a route to the DNS server? Do I have the correct IP address for the DNS server? Because DNS, obviously a big deal in order to do those things. OSPF, neighbor adjacencies, could be a configuration problem, appropriate commands to isolate, solve the problems. Mostly those are going to be the show commands. And the neighbor adjacencies, there where the timers had to match. And we did the show interfaces, show IP OSPF interfaces will show us the interfaces, the timers are there. Areas had to match. And if we had passwords configured, obviously they've got to match in order for the adjacents. And we got to be on the same subnet. We got to be able to talk to each other. Can you ping that interface? Can they actually talk? EigrpJune, autonomous system numbers have to match, and the K values have to match. And they got to be on the same IP networks too, the same IP subnet. So we've got to have the same subnet mask length for these things, the same network, be on the same network. Can they ping each other? Can they talk to each other before we go from one to the other? Static routing issues, if they say on both those, if a static route is missing, if end-to-end connectivity is a problem, ping your own interface. And this is missing in the route table. Ping your own interface and then the other devices on the directly connected networks. Or is my TCP/IP stack working? Is my NIC working? Do I have good connectivity? Is the cable good? Or are the tabs, did it back out? Is it connected? All sorts of things can happen with these and the troubleshooting. After you verified the direct connectivity, begin testing connectivity to remote devices. Ping me, 127.0.0.1, ping my IP address, ping my default gateway, ping, and usually I always like to do just the other side of the default gateway and then something farther out. Can I get there? Can I get back? Events that can change the network status, failure of an interface, connection dropped by the service provider over saturated links, incorrect configuration information. And if an interface goes down, that can change the network status, failure of an interface, the interface failure is going to take that route out of the route table because it's going to. A couple of kind of what goes on here, inter VLAN routing issues, the absence of VLAN interfaces, hosts not configured to use the VLAN interface as the default gateway, and the inter VLAN here is the switch virtual interfaces that we're talking about. We don't have them. And when you do these things, the VLANs that we're trying to connect one to the other have to be on the multi-layer device, the layer 3 switch. Because if they're not, they can't get in the trunk. If they can't get in the trunk, you can't return the answer. Remote switches have no pathway to the VLAN interfaces, and in the absence of a VLAN, when trying to create a VLAN interface, the VLAN itself doesn't exist. Doesn't have to have any ports on it, but we need it to be there in that absence of routes on the layer 3 switch route table. Other issues down here, a speed mismatch. The router and the switch both use the speed interface subcommand to set the speed, and this is probably something that's unnecessary. Maybe 15 years ago, and I could probably come up with a different year each time, but it was a long time ago, Cisco had an issue with the auto negotiate. They haven't had an issue with auto negotiate in years. Auto negotiate is the default configuration for NICs and for switches. What it does is automatically negotiates the speed and duplex for whatever is allowed, for the one that is the least capable. If I put a half duplex 10 megabit per second NIC in a system, plug it into a switch, that's what it's going to negotiate. And you notice that on the port speed we see 10/100/1000, 10 meg, 100 meg, gigabit. It will negotiate all of those speeds, and we're going to get to 10 gig here pretty soon, I'm pretty sure with that. Shutdown, it's configured, the interfaces are configured in a shutdown mode. And when we go to the show IP interface brief, it'll say administratively down, down, down. We have to give the no shutdown command after the IP addresses are assigned before the interface is going to become active. Error disabled switch. The neighboring switch port uses port security, and we'll do port security next week, and has put the port in an error disabled state. Error disable is effectively shut down. It's not going to send any data back and forth. But in order to get it back up, it's a little bit different process. But that is something that we will do when we do port security in here. The error disable state, no cable or a bad cable. The router has no cable installed, or the cable pinouts are incorrect. The router will be in down, down. And you may laugh at that and say, hey, it's not going to happen. I used to do this to classes just to try to get them to think about the physical connectivity and the data flow. I go in and disconnect all the wiring from the computer to the whole pass, and it was all in the room. It wasn't like it took more than about a minute in order to connect it back up. Connect to the NIC, go connect your device into the switch so that you could get there. So no cable, bad cable. It's something that can happen. It gets unplugged, and people aren't trained to recognize the issues. And you can look at yours and it says that, and you will get an indicator on Windows that says that we have an issue with that. So you might start looking at those things, but that's not always going to be the case with the users, because that's not what they do. They just come in and turn the machine on and log in, do their job, and then go home. Maybe go get a virus for you or something like that. Inability to access the remote resources, common OSPF, general connectivity issues between the networks, wrong protocols. The troubleshooting OSPF, the commands that we've been looking at, show IP OSPF, may not be configured on one of the routers. You can do the show IP OSPF, you can show IP protocols. The show IP protocols will show you, and this one's not OSPF obviously, will show you which protocols and the information about that protocol. Protocols, and this is what we looked at with EigrpJune, Autonomous System 20, outgoing redistributing for EigrpJune 20. So we got a lot of indications in here. We should know what our autonomous system number is. The K values are here. They do have to match. The router ID is here. We can see it. If it's not what we want, we can go change it. The administrative distance, the cost here, the maximum paths, and the maximum paths, these are the maximum equal cost paths that we can have. If you want more, you can configure up to 8, I believe. It's the maximum hop count, and then the variance here, a variance of 1. The variance, the difference between the different bandwidths of the interfaces, how great can it be before we would have an unequal cost balance the flow here. And the 1 is going to be equal cost for these things. And the auto summarization is disabled on this thing. The routing for which networks are we routing for? And this will tell us if we could go in here and look and say, oh, I forgot to advertise a route. I didn't do that. I thought I had that advertised. You can see that pretty quickly, or you can go into the show run and do it there and look under your network statement and see what's saying. Show IP-OSPF interface. I'll go back to this thing to show these things again. And this is where, well, this is not OSPF, so it's not going to work. So we could show the IP-EigrpJune interface, I guess. Interfaces, and it just tells us which interfaces are there. The OSPF gave us the timers, and that's where you would find if your timers were matching on this thing. Show interface, the MTU mismatch, the maximum transmission unit. And a lot of these things, unless somebody's fool with it, unless you mess with it, these things shouldn't change. It's, if they did change, then we may have a bigger issue that we need to get into the logging and see who's been on. Duplicate router IDs will not be a good situation because we'll have the destination, 2 different physical locations with the same logical. This is basically the same table. OSPF's not configured show, and I think that show interface. I think these are all the same. Maybe a little bit, I think a little bit easier to read if you want to take that. EIGRP issues, some of the common things, I got to go back to it. The inability to access remote resources, and that's always going to be the issue with the routing protocols. General connectivity issues between networks, which means that routing's not working. Autonomous system numbers don't match. Now that is something that can happen, and that used to be actually, when we did labs, that was a certification question. The junior administrator just put in this new EigrpJune router and it's not working. What's the problem? You're going to go in and use the show commands to find what the problem is, and most of the time it was the autonomous system number didn't match. You could also get a K value mismatch. Neighbor authentication, if we have authentication enabled on the devices. Show IP-EigrpJune neighbors command doesn't list 1 or more of the expected neighbors. If ping is successful, the neighbor verification checks. Show the interfaces. This is all the same thing. Autonomous system number, can I ping it? Are we on the same network? Do the K values match? All of those things we've got to check. The EigrpJune authentication, K values, autonomous system number, same subnet. All of those things have to. EigrpV6, for that router doesn't have any routes to a given subnet. If the routers with the interfaces that are directly connected to the IPv6 prefix or subnet, a router will need to have EigrpIPv6 enabled on the interface. And that is what we looked at in the configuration. We have to start an autonomous system number, and then we configure the protocol on the interface with the autonomous system number. Check the EigrpNeighbor neighbor relationship for all routers between the local router and the routers with an interface connected to the prefix or the subnet. Doesn't have anything, has a route, but it appears to be the wrong or suboptimal route. This is one of those that, yeah, maybe it's really not. Check the interface bandwidth and delay settings, and we can configure the bandwidth on the interfaces, so we can lower it or raise it, kind of lie to the system. In particular, check the lowest bandwidth that we have from us to the destination. So maybe it really is the optimal route, and we just missed or another path, or the path that we expected for some reason has slowed down, it's gotten bogged down. Some delays that it goes in, because delay is one of the big factors that EigrpJune is going to use. Most troubleshooting revolves around neighbor relationships. There are 2 problems that occur on the interfaces. When the IP-EigrpJune autonomous system as an interface command is omitted on the interface, that has no possible neighbors, it can be overlooked. When this omission will not impact the neighbors, it will mean that the EigrpJune for IPv6 is not enabled on that interface. It's not going to advertise that network is what that's saying. So even if we don't have anything for it to communicate with, if we want it to be advertised and the route available to that interface, to that network, we still have to enable the EigrpJune on the interface. And EigrpJune v6 is enabled on the interface. That the IPv6 EigrpJune is an interface command, even if an interface has no possible neighbors. And when an interface is made passive to the IPv6 process, and if a potential neighbor is connected to the link, it'll prevent the two routers from becoming neighbors. The passive interface command will stop the communication for these things. Check to be sure that none of them are in a passive state. And I think it show protocols, either show protocols or show the interfaces. And I think it show protocols will tell you whether it's passive, which interfaces have been configured as passive interfaces. I think that brings us up